Problem set 1, number 2. We're dropping a 10 kilogram box on a frictionless track and we want to know the final velocity. Let's do the analysis first. The sum of the energy changes have to be 0. We've got to conserve energy. So what do we say for that? Well, we know that we start with potential energy. So the potential energy must be turning to kinetic energy, right? Plus other losses, right? It's frictionless, so nothing's being changed to heat. It looks like a perfect conversion. So this should be straightforward. Change in momentum is 0. Okay, so there is a change in momentum. When this comes off the end, it's moving in this direction where V0 was 0. So it's gained this momentum in this direction. Who is the box exchanging momentum with? We know if this was a track on wheels and that box came off, the delta P it received in this direction would be equal to the impulse, the change in momentum of the track on wheels. But it's very big. It's the whole Earth. So yes, the whole Earth is getting an impulse in this direction, but because the mass of the Earth is so big, you don't notice it. Okay, so this may not be very helpful to us, but it will be in the next problem. The sum of the forces is equal to mass times acceleration. Okay, so we have a force from the track and we don't know the angle, so that's going to be difficult to do, and it's changing all along. I think it'll be a mess. Motion. Do we know the acceleration? We don't. Do we know the speed? We don't. That's what we're trying to find out. So none of these equations of motion I think will be helpful to us. So let's jump on this. The potential energy at the beginning is mgh, and it turns into kinetic energy 1/2 mv squared. We can solve for the velocity. First thing we notice is mass doesn't matter, and that makes sense. If we had two masses next to each other, roped together, they'd come down at the same speed as if they were alone. If you double the mass, yeah, you double the kinetic energy it needs, but you double the potential energy it has. And so we can solve for the final velocity. It's going to equal 2 times gh, and don't forget, we need to take the square root. So we substitute in 2 times 10 meters per second squared times the 50 meters to the 1/2 power. That's 20 times 50 is 1,000 meters squared per second squared. That's okay because I have to take the square root, and that yields meters per second. What's the square root of 1,000? Well, it's about 30, because 30 times 30 is 900. How about 31? 31, we get an extra factor of 30 twice, so that's going to be about 960. We can see from that 32 is going to be too big. So it's somewhere around 31 meters per second, 30 meters per second. That's good. So for 2c, you're just taking different roots. It's all frictionless. All of this holds the same. The same potential energy in the beginning is turning to the same kinetic energy at the end. So we know that the speed at the bottom is going to be the same regardless of the route you take. Now, how about the amount of time it takes to get to the bottom? Well, we want to take a look at what time is, because the speed is equal to dx dt, right? Or dl dt, where this is the length. And so the change in time is just going to equal dl divided by the speed. And it's true, these two are a little bit longer, but let's take a look at the speed. If we cut this at any given point, where this is track A, B, and C, we can see that the potential energy of A is bigger than B is bigger than C. So anywhere you are here, this track has a higher potential energy, which means, because the potential energy is changing to kinetic energy, this has the highest kinetic energy all the time, and this is second highest and that the least. So the ball on this track is always going fastest. Now it's true, we could have made this super, super long. It goes all the way down 20 floors and then comes up. then we could say the length is the bigger issue. Even if you're going faster, it's going to take longer. But that is not the overwhelming factor here. And so you can say, if we drop 3 balls at a time, one on this track, one on this track, one on this track, this ball would be going the fastest. Which makes you realize, if the ball was here, this ball wouldn't be here. It would be here because it's going faster. And this ball would be down here. So this one has lost even more potential energy and has gained more kinetic energy, is going even faster still. And that's what we saw. Now some gratuitous calculus for you fanatics. What if you really wanted to know exactly what the time was, and we wanted to get an exact measurement of this? You'd recognize that we would start with this formula and then integrate over each little bit of length. So here's a little bit of length. We know there's a certain amount of time it takes, and we integrate all along that curved surface, a line integral. Whoa, this is going to be crazy. So we know that dl is equal to the square root of dx squared plus dy squared. And that is equal to the square root of dx squared plus dy dx squared dx squared. I can pull out the dx, and then what I have is dx times the square root of 1 plus y prime squared. So now what I've done is I've turned this into a differential that I can integrate along, but I don't know the function y. I didn't even tell you. I could use this, it's a straight line. But we have an unknown function, and then I need to know its derivative. How about the speed? What we know is the kinetic energy is equal to the total energy, E naught, which is just mg h naught, where h is the 50 meters, that total energy minus mg, the height that I'm at any given time, and this is a function of x. So I'm going to change that height to y. So now I know, and again, this is y as a function of x. So at any given spot, I can find my height. That will tell me the potential energy I have left. This will tell me the total kinetic energy I have, and I know that's equal to 1/2 mv squared. And maybe I want to simplify things by replacing this with mgh naught. And so now I have mg times h naught minus y is equal to 1/2 mv squared. And I can solve for v. V is then equal to, the m's cancel, is equal to 2g h naught minus y to the 1/2 power. Now we're ready to slam that into the integral. You're going to love it. So the time, the total amount of time, is equal to the integral of dl, which is dx times the square root of 1 minus y prime squared, divided by the speed, which is 2g h naught minus y to the 1/2 power. And so all you have to do is do the integral from a to b, where this is a and that's b, and you're done. So we don't know the function, and we don't know its derivative. I haven't given you that, so we can't do it, but this is how the theoretical mathematical physicist would have done it. Okay, 3a, we drop the box, and we want to know what happens with the Earth. Now we recognize the importance of this delta P must be equal to 0. This would be more obvious if the two bodies were closer to the same mass, maybe like the Earth and the Moon. If you stop the Moon from revolving around the Earth, and you just put them out in space, yeah, the Moon would accelerate in this direction, and the Earth would accelerate in this direction, something like this. Such that the impulse that the Moon got, delta P, would be equal to the impulse that the Earth got. And so what we see here is, yes, the sum of the change of momentum must be 0. As the box accelerates down, the Earth accelerates upward. And so the change in momentum of the Earth must equal the change in momentum of the box, or mass of the box times the velocity of the box that it picks up right before it hits, going very fast, is equal to the mass of the Earth times the velocity of the Earth as the Earth is moving up in this direction. So the velocity of the Earth is just equal to the velocity of the box times the ratio of the masses, the mass of the box and the mass of the Earth. Right? The mass of the Earth is way bigger than the mass of the box. Right? This winds up being what? 31 meters per second times, what's this? 10 kilograms. And the mass of the Earth is about 6 times 10 to the 24th kilograms. That's just a ratio, it's unitless. And I like this because that's Avogadro's number. Right? So this ratio is 1 over 6 times 10 to the 23rd. I make my life easier doing scientific notation. So this is 3.1 times 10 to the 1 meters per second divided by 6 times 10 to the 23rd, that ratio. And so this is 0.5, and that is 10 to the 22nd, which is equal to 5 times 10 to the negative 23 meters per second. So how about the kinetic energy? Well, the Earth has a very low velocity moving upwards, but a very large mass. So, but we square the velocity. So we could just say the kinetic energy of the Earth is equal to 1/2 mass of the Earth times the velocity of the Earth squared. And I could solve it that way, but I'm going to be a little trickier. What we can also do is say the kinetic energy of the Earth is equal to the momentum of the Earth over 2 times the mass of the Earth. Right? And the reason, the momentum of the Earth squared over 2 times the mass of the Earth. And the reason I like that is because I already have the kinetic energy for the box. That's just equal to mgh, where this is the initial height of the box, because all that potential energy of the box turned into kinetic energy. And I know that the box and the Earth must have equal and opposite momentum. So I can just find this and say, yes, this is 10 kg, this is 10 meters per second squared, and this is 50 meters. So that's equal to 5 times 10 to the third, 5,000 kilogram meter squared per second squared is equal to 5,000 joules. And then I can say, look, the kinetic energy is proportional to 1 over the mass. So the kinetic energy of the Earth must equal the kinetic energy of the box times the mass of the box divided by the mass of the Earth. Right? And I like that. This is just 5 times 10 to the third joules times this ratio, which I already know is 1 over Avogadro's number, 6 times 10 to the 23rd. And then we can say, all right, yeah, 6 is about 5, and I've got 10 to the third and 10 to the 20th is about 10 to the negative 20 joules. Right? So this is the energy the box gets, this is the energy the big old Earth gets. It's not important.